Let us first see how the mean and variance of xn behaves as n tends to infinity. Let us state it as a lemma. We have limit n tends to infinity en star of xn is equal to r minus sigma square by 2 t, and limit n tends to infinity variance of xn. So these are the variance and expectations under the risk neutral probability with respect to the partition Tn, right? And that is given by sigma square capital T. Let us see how these expressions come. So let us first prove the limiting case of the mean of xn. That is, we'll prove the equation star. Let us first try to compute the expectation of yn, because xn is nothing but the sum of yns. Therefore, if we know what is the expectation of yn, then from there we will get an expression for the expectation of xn. The advantage of that is because yn probabilities are given to us, and yn has exactly two outcomes, either up or down, and we know how the probability is given in both the cases. Therefore, we can immediately write the expectation of yn, and that is given by, at each time level k, is given by Pn star into Un, that is taken as sigma root delta Tn. I'm sorry, there should be a log here. Please change this in your notes. It is log Un, because you can see that ykn is given by log of sk, where sk is either un or dn. Therefore, it should be log of this, and un is e to the power of this. Therefore, log of e will go and you will have this. So this is correct, but this has to be changed. Plus alpha delta Tn plus 1 minus Pn star into minus sigma root delta Tn plus beta delta Tn, right? So that can be written as, I'm just rewriting this as 2Pn star minus 1 sigma root delta Tn plus delta Tn. If I take common, I have alpha Pn star plus beta 1 minus Pn star. So just rewriting this expression. And if you recall, in the previous lemma, when we were proving the limiting case of Pn star, we have derived this expression, right? And then only we took limit as n tends to infinity, and we showed that this expression goes to 0, and that is how we have proved Pn star to be equal to 1 by 2. So we can just substitute that expression here. Remember that expression has a sigma root delta Tn in the denominator. That gets cancelled with this one, and you have r minus sigma square by 2 minus alpha plus beta by 2 into delta Tn plus a big expression which goes to 0 slightly faster than how delta Tn goes to 0, divided by 1 plus some big expression which goes to 0 slightly more than a constant. Okay, even delta Tn to the power of 0.0001 also can go to 0 slightly faster than constant, right? So therefore, anything which goes to 0 can be written like this as n tends to infinity. So that takes care of this term. And this term again, I will write as plus delta Tn into alpha plus beta by 2 plus a order of 1. That comes directly from our previous lemma, because we know that as n tends to infinity, Pn star goes to 1 by 2. So I'm just putting 1 by 2 plus something goes to 0. Okay, that is why we had as limit n tends to infinity, Pn star equal to 1 by 2. Okay, so that's what I'm just writing here. I'm just putting 1 by 2 here, and that gives me the first term. And of course, I have not physically taken n tending to infinity, therefore I cannot just write this alone. So I wrote there is something which definitely goes to 0 as n tends to infinity. So that's what it means. So if we take physically as n tends to infinity, then this term goes to 0. Okay. And similarly here also everything goes to 0. You have to be careful with that. I'm not physically taking n tends to infinity, but I'm writing in the limiting case how the expression looks like. The important expressions alone I will keep. Those which are not important for me in taking the limit, I will use a notation like this and just freeze them. I don't care what those expressions are, whatever may be the expression. When I take n tending to infinity, they will go off surely without giving me any problem. Whereas these terms also may go off, but how they go off, that we have to analyze. Okay. So this is what finally we got for expectation of yn at the kth time level, right? This can further be simplified into En star of Yn. It's not actually a simplification, but I am just freezing all unwanted terms into small o notation. It's just a notation. And then keeping only those which are going to contribute in my limit. Okay. Sorry, this is actually the common delta t. Okay. Now, this expression can be rewritten as En star of Ykn is equal to the first term, or minus sigma square by 2 into delta Tn. Remember, there is a delta Tn into alpha plus beta by 2, and there is the same term with a minus sign here. That has some expression in the denominator also, but as n tends to infinity, it behaves more like 1. Therefore, I can just club them off, okay, into this term. And similarly, this entire thing can come into this term. Therefore, everything else will go as fast as how delta Tn goes to 0, okay. Whenever you use this notation, you have to clearly mention that as n tends to infinity, okay. This you have to mention, otherwise I may cut mark, okay. Whenever you use this notation, small o or similarly big O, there's one more concept called big O. So these are the notations to compare two sequences or two objects which are tending to some limit, okay. Now they tell us how fast these sequences go to that limit. Okay, in the here the limit is 0, and the sequence is something which is depending on n, and the sequence goes to 0 as n tends to infinity. Now the question is how fast they go to 0. Okay, small o means small o of any sequence you give here. It means the expression which is given here will go at least slightly faster than what is written here. Okay, say for instance, delta Tn is a sequence, and delta t n to the power of say 1.001 is a sequence, right? So this can be written as actually small o of delta t, okay, because it definitely goes slightly faster than this, right? So any expression, okay, so it can be a big expression also, as long as it goes slightly faster than delta tn, you will just simply write it. It's a more like a notational convention, and it is conveniently written like that. So you look at this term, this is independent of k, right? Therefore, when you bring this expression into xn, that is the expectation of xn, it's very easy. Therefore, expectation of xn is nothing but the summation of all these terms, because the linearity of expectation. So therefore, that everybody is independent of n. Therefore, you will have n times e star n of yn at the kth level. That you can simply write it at some level. Everybody is identically uh, distributed. Therefore, it doesn't matter what index you pick up. Okay, I'll just pick up the first index and write, and everybody else will be same. En star of y and 2, 3, 4, everybody will be same. Therefore, they will come out with one of the index you can fix. And then you have a summation, say k equal to 1 to n. So that will bring you a n here. So that gives me n r minus sigma square by 2 delta tn plus small o of delta tn, right? So since I'm writing this notation, I have to always write n tending to infinity. Always I have to write wherever I write this small o notation. Now you see, what is this? This is nothing but delta tn is t by n, right? So this n and then this n will get cancelled, and therefore I will have r minus sigma square by 2 capital T plus, you see, this is t by n, okay, n is going off. Therefore, this will now behave more like a constant term, okay, and already this sequence is going slightly faster than delta tn to 0, right? Therefore, if you multiply by n, then it will go one order, it will lose, because you are multiplying with n. See, if you have t to the power t by n, and that goes slightly faster than this, means something like, as I told you, 1.001, like that it may be. Therefore, when you cancel one n, then it will be 0.00. So it still goes slightly, it still goes to 0, but slightly faster than a constant. Okay, constant of course won't go to 0. That is how it is written as n tends to infinity. Okay, because you are just cancelling one order by this, therefore it becomes one order less, therefore it becomes a constant. But this term goes to 0 slightly faster than a constant. Constant never goes to 0. So that proves your first problem. Next, let us prove the limiting case of variance of xn. Since yks are identically distributed, we have variance of xn is equal to n times variance of yks. Okay, so just to fix the index, I will put it as 1 here, and that is by definition expectation of y1 of n square minus e star n of y1 n the whole square, right? So we have computed this, therefore you just have to take the square of it. Let us compute the first term. That is equal to log un plus log ud into expectation of y1 of n, which we already know, minus log un into log, sorry, this is dn. Okay, so how it comes? Note, if you have x as some random variable which takes value u with probability p and d with probability 1 minus p, then your expectation of x is obviously given by p into u plus 1 minus p into d, right? And how e of x square is given? E of x square is given as u square p plus d square into 1 minus p. That you can write as, so you just can simplify or rewrite this expression to get u plus d into e of x minus ud. Okay, so you can write this. That's what I have used here. You recall that y1 and similarly all the yks takes either the value log un or log dn with probability p star n and 1 minus p star n respectively. Therefore, it exactly comes into this case, and therefore its expectation of x square, this can be simplified to u plus d into e of x minus ud. That I am just using it here. So therefore, e star n of y1 square can be written as, I'm just putting the expressions for these things. Okay, so you have alpha plus beta delta tn into, we know this, just now we have calculated, I can put that here, r minus sigma square by 2 delta tn plus some expression which goes slightly faster than delta tn. Therefore, I have to write as n tends to infinity minus this term. Again, you know what is un and what is dn, and that if you just supply here, tn plus alpha delta tn into minus sigma root delta tn plus beta delta tn as n tends to infinity. And that again you can just club all the terms together and bring only certain terms which are like this into this will give you order 1. See, this and this will give you order 2, therefore they are higher order, right? So you have and therefore this entire thing, this into this will give a higher order term, so you will club them all together. So only this term I will keep sigma square delta tn plus all other terms, either they go with say these all will go with delta t square, whereas this will go with this multiplied with this, and similarly this multiplied with this will go with delta tn to the power of 1 plus 1 by 2, right? That is 3 by 2 and so on. So whatever it is, they will go faster than tn. That's what is given. This goes with speed exactly tn. This goes something faster than tn as n tends to infinity. See, we don't write all this explicitly because they anyway will go to 0. Okay, so why to put effort to write them? That is the idea. So substitute this into your expression here. You already know this. Now we have computed this. Therefore, we can substitute this. Variance of xn equal to n times sigma square delta Tn plus small o of delta Tn. That is your e of x square term minus e of x the whole power whole square, that we already know how it looks like. Therefore, that is delta Tn plus big O of delta Tn the whole square, right? So that's how they look like, whole square. And that can be now again this with this one order it will reduce. Therefore, it is sigma square capital T. Therefore, this will not go to 0. Therefore, you should, that is why we kept this carefully outside this frozen term. Okay, this frozen term anyway going more than a linear convergence. Therefore, when you reduce it one order by multiplying with n, because this is t by n, you should remember always this, it still goes to 0. And similarly, you can see here you have a delta Tn, but that is squared here. Okay, therefore, when you reduce it by one order, anyway, it will also go to 0. And this is anyway going to 0 slightly faster than delta Tn, and that is raised to 2. Therefore, it is going slightly faster than something like delta Tn square. Therefore, you are only reducing the order one less. Therefore, they will also, all these rest of the things will go to surely 0, slightly faster than delta Tn, and therefore as n tends to infinity, here also as n tends to infinity. And that gives me, if I take n, now physically if I take n tending to infinity, this will go to 0, and therefore I will have this. Therefore, limit, now I am physically taking n tending to infinity, variance n of xn is equal to, when I take limit on this side, this term is free from n, therefore it will not get affected, plus this term is anyway going to 0 as n tends to infinity, so they don't come into your expression, and this proves the lemma. The next property is a variation of central limit theorem, and therefore we will omit the proof. We will only give the statement of the property in the form of a lemma. The property says that the sequence of random variables, we called the random variables xn's, are defined by log pi k equal to 1 to n sk bar, which can be written as the sum of ykn's, and these sk bars are the numerical values of the up and down of the stock. So the property says that this sequence converges in distribution to a random variable x, which has a normal distribution. Generally, we denote the normal distribution by n, whose mean is r minus sigma square by 2 into capital T, and the variance is sigma square capital T. So this is what the lemma says. We'll omit the proof of this lemma for our course. Using the above two properties, we can now state the Black-Scholes price model for put option. We will state it in the form of a theorem. Remember, the pricing model that we are going to state is for a put option. The statement says that let H naught N be the price of the European K strike put option with period 0 to capital T partitioned into n sub periods. Let us consider the parameters un, dn, and r as given by, recall, we have taken them as in a general form, right? So it is given by un is equal to exponential of sigma root delta Tn plus alpha delta Tn, and R is in such a way that 1 plus Rn is equal to e power or delta Tn. So these are the ways we have defined the parameters. With all this, we can take the limit n tending to infinity, thereby we are coming to the continuous time model of P naught of n is given by P naught, where P naught is E star of e power minus RT PT. PT is the payoff of the put option, and E is the expectation with respect to the probability space on which the random variable X is defined, where PT is the payoff. Since we are working with put option, it is maximum of 0 comma k minus s naught e power x, and x is normally distributed with mean r minus sigma square by 2 capital T and variance sigma square capital. So this is the statement in which this expression is finally the Black-Scholes pricing model. We can say that the pricing P naught is called the Black-Scholes pricing model. Recall that in this property we say that xn converges in distribution. But if you recall, the convergence in distribution of random variables is defined only in terms of the convergence of the respective distribution. This you would have studied in your probability course, and therefore consequently it is not necessary that the random variables are defined on the same probability space. For instance, if xn is defined in the probability space as n fn comma pn say, and x is defined on the probability space as f comma p, then if you recall, by definition xn converges to x in distribution if and only if limit n tends to infinity en of phi of xn is equal to e of phi of x for all phi in the space of all bounded continuous functions on Rm for some, where En is the expectation with respect to the probability measure Pn, and E is the expectation with respect to the probability measure P. So we used this property to conclude that the convergence of the sequence P naught, that is this one, this sequence P naught n to this. So in the proof, of course, we are not giving the proof of this theorem also, but in the proof we will be using this condition. Okay. So using this condition, we are obtaining this. Here you can see that the condition says that the expectation of some bounded continuous function. Okay. Then only you have this result. That is why we have taken our option as a put option, because in this case your argument in the expectation, you can see that e power minus rt is a bounded continuous function. Now pt, which is given like this, is also a bounded continuous function provided we work with put option. That is why we have taken first the put option and established the Black-Scholes model for the put option.